Okay.
So good morning, everybody. Welcome to our weekly machine learning seminar. Today we'll have a pleasure to have a talk from Onkar Jadhav, who is a postdoctoral researcher at the University of Luxembourg in our group, and who will present a topic that is shown on the screen already. So Onkar, the virtual floor is yours. Please go ahead.
Thank you very much, Jakub, for inviting me to this machine learning seminar. So today I'm going to talk about the parametric model order reduction with adaptive greedy approach for parameter sampling. This work I did during my PhD, and this is some of part of the work actually. So the presentation is arranged as follows. First, I will introduce you to the developed model order reduction framework, followed by SRIN analysis, and finally with the obtained results for two numerical examples considering financial application, I will conclude this presentation. So we have to solve high dimensional models in multiple fields ranging from engineering, finance to biological sciences. And solving these high dimensional parametric partial differential equations uh, are obviously computationally costly, and which creates a need for an efficient computational performance. Model order reduction is a technique that reduces the computational complexity of developed mathematical models. So it does so by replacing or by approximating the full order model of order M with some reduced order model of order D, such that D is very, very less than M. And since D is very, very less than M, this reduced order model is much cheaper to solve than the full order model, and that provides us our necessary computational advantage. So the developed model order reduction frameworks look something like this. First, we start with the discretization of the partial differential equation, either using finite difference method, finite element method, or even a finite volume method. And in my work, I have used a projection-based technique called proper orthogonal decomposition, which relies on the method of snapshots in order to generate a reduced order model. And this method demands us to solve this discretized full order model for some training parameters. And thus, to select these training parameters, I have implemented either classical greedy sampling approach or adaptive greedy sampling approach. Now, let me explain you this model order reduction framework in a bit more detail. So let's first start with the discretization. So consider a discretization of our PDE generates a parametric full order model, that is this linear system of equation which we have to solve at each time step with an appropriate boundary condition and a known terminal condition. And here you can see that these matrices A and B are the parameter dependent matrices of order M, where this row is the S parameter, and we have to solve this full order model for, let's say, in the case of finance, for 10,000 parameters. And this is obviously computationally costly. So we can develop a reduced order model, something like this. We can project that full order model onto some projection subspace, here denoted with the Q, called reduced order basis, which gives us this reduced order model of dimension D. And since, as I said earlier, this D is very, very less than M, this reduced order model is much cheaper to solve, which provides us our necessary computational speedup. Now, the obvious question is how to obtain this reduced order basis in order to get an acceptable reduced order model. And for that, I have implemented a method called proper orthogonal decomposition, which relies on the method of snapshots. And these snapshots are nothing but the state solutions calculated by solving the full order model for some training parameters, let's say from row 1 to row L. Now we combine these snapshots into a single matrix called snapshot matrix and compute its truncated singular value decomposition as shown over here. Now the reduced order basis Q consists of D left singular vectors that minimize the projection error. I will talk about the errors associated with the model order reduction in a bit more details later on. But before that, you might have guessed so far that the quality of this reduced order basis Q mainly depends on these training parameters which we use to obtain the snapshot. So it is necessary to select these parameters sufficiently and more carefully. And one could implement a normal uniform sampling or random sampling, but they might neglect the vital parameters within our parameter space. And thus, to overcome these problems, generally classical greedy sampling approaches are used. So here the idea is we select a parameter group that maximizes the relative error between the full order model and the reduced order model. So in some sense, we are picking bad apples from our parameter space, and we are putting that information into our snapshot matrix. So making our snapshot matrix much more richer. So in the next iteration, we will get a better reduced order basis. However, there is one problem. This relative error entails the solution for the full order model, and which is obviously computationally costly. And that's why it is usually replaced with some error estimator like residual error. So at each grid iteration, the algorithm chooses a parameter group that maximizes the residual error. And once we have enough number of parameters, then we can construct a snapshot matrix and compute a reduced order basis by computing the truncated singular value decomposition of our snapshot matrix, as I explained you before. However, this classical greedy sampling approach has some drawbacks, and that's why I developed an adaptive greedy sampling approach. It is, first of all, it is not feasible to calculate the error estimator values for the entire parameter space P. And that's why this classical greedy sampling algorithm is usually trained on some subset PCAF of cardinality C, which is usually selected randomly. And these random selections may neglect the vital parameters within our parameter space P. And that's why I developed an adaptive greedy sampling approach, which uses a surrogate model instead of the actual error estimator to adaptively locate the important parameter groups much faster. One could develop a surrogate model using any technique and for this presentation, I will explain you the surrogate model based on principal component regression approach in the next few slides. But before that, let me introduce you to the developed adaptive greedy sampling approach in brief. So what we are interested in is this parameter set PCAP, right? So the adaptive greedy sampling approach works something like this. First, we start by computing the error estimator over some subset PCAP 0 of cardinality C0 such that C0 is less than C. Now we use these error estimator values in order to construct a surrogate model. And we solve the surrogate model for the entire parameter space P. Now you can see here that as we are solving the surrogate model instead of error estimator for the entire parameter space P, which is much cheaper to solve, this method is computationally advantageous. And now we select the first CK parameter groups that maximizes the surrogate model. And we keep on repeating this process until the total cardinality of our parameter set PCAP reaches C. And once we have our desired parameter set PCAP, we can determine the optimal parameter that maximizes the residual error. And once we have enough number of parameters, we can construct a snapshot matrix and obtain a reduced order basis to generate the reduced order model, as I explained you before. So you can see at each kit iteration, we have to build one surrogate model for the error estimator. And one could consider a simple multi-regression model as shown over here, where this least square approach gives us our necessary regression coefficients neta, but there were two main problems. First of all, we have a data matrix at each kth iteration of order Ck cross M, where Ck is the number of parameters and M is the number of 10R points. So if this Ck is almost equal to M, then there might be a problem of overfitting. And if this Ck is less than M, then there is no guarantee that this least square approach will give us the unique solutions. And thus, to overcome these problems, I am suggesting here the principal component regression technique. This is again a projection-based technique which replaces the M variable with P principal components. And for that, we compute a singular value decomposition of our data matrix Pcap K, as shown over here, where the columns of the matrix Pcap K Scicap are the principal components. Now we regress our error estimator values on the first P principal components to obtain the regression coefficients omega. And then the PCR estimates of our desired regression coefficient neta can be obtained by back projecting this regression coefficients omega onto the psi cap P matrix as shown over here. And once we have our regression coefficients, we can construct a surrogate model, which we use during the adaptive greedy sampling approach. Another interesting problem I came across while developing this adaptive greedy approach was monitoring its convergence. So in order to monitor the convergence of this adaptive greedy sampling algorithm, we have to specify the maximum error estimator tolerance. But this error estimator usually depends on some error bound, which may not be tight or may not exist. And thus, I developed an approximate model for the relative error as the function of the error estimator. And this is quite simple to implement considering this developed adaptive greedy approach. So, which is explained in this flowchart. So, at each greedy iteration, we are already selecting an optimal parameter in order to, and we are solving a full order model for it in order to update our snapshot matrix. So, before updation, we compute a relative error between the full order model and the current reduced order model and the corresponding error estimator value. Now we update our snapshot matrix and compute a new reduced order basis and generate a new reduced order model. So after updation, we again compute a relative error between the full order model and the new generated reduced order model and the corresponding error estimator. So you can see in some sense at each greedy iteration, I have this error set EP, which looks something like this, having relative errors and the error estimator before and after updation. So now you can use this error set in order to construct an approximate relative error model as the function of error estimator. And here you can see that I've considered a linear model, and one could consider a non-linear model here as well. But for my finance application, this linear model assumption was enough, which I will show you later on with the obtained results. So all these algorithms which I've explained you so far are associated with some numerical errors. For example, the discretization of our partial differential equation generates a discretization error. Then the model order reduction approach has its own errors. Then there are sampling errors associated with the sampling algorithms. However, in my work, I've considered partial differential equation as the true solution. So the modeling errors has been neglected. And all algorithms are developed in such a way that the total simulation error is less than some specified tolerance. Today, I'm not going to talk about the discretization error, but let's talk about the model order reduction error and the sampling error in bit more details. So as I said earlier, I have used a projection-based technique called proper orthogonal decomposition, which demands us to compute a truncated singular value decomposition of our snapshot matrix. And in order to generate a reduced order basis, we select only D left singular vectors out of K left singular vectors. Now this neglected K minus D left singular vectors leads to the projection error. And this projection error can be represented in the form of neglected singular values, which is nothing but the sum of squared of neglected singular values while generating the reduced order basis, as shown over here. Also, the relative error between the full order model and the reduced order model tells us that how well the reduced order model approximates the full order model. And all algorithms are developed in such a way that the dimension of the reduced order basis D is chosen such that the relative error and the projection error are minimized. So another interesting problem I came across during the development of this model order reduction approach was the computational complexity of series of singular value decompositions. At each ith greedy iteration, we have a snapshot matrix of order m cross ti. And you may know that the computational complexity of singular value decomposition is m ti square. So after I iterations, the computational complexity of series of singular value decompositions will be mt square I cube. And you can see that this computational complexity is increasing with each proceeding iteration. And this is quite computationally costly, and that's why I've implemented a truncated singular value decomposition based on randomized algorithms. And this provides a really nice quite speed up for my application, which I will show you later on with the obtained results. But first, let me explain you this randomized SVD in brief. So consider an approximate basis G. for the range of our data matrix V cap. Now we compute a reduced matrix V tilde such that G transpose into V cap as shown over here. Now we compute a compact SVD of this reduced matrix V tilde. And as we are computing a singular value decomposition of this reduced matrix V tilde, we achieve our necessary computational speed. And finally, we can set our left singular vector matrix phi as G into phi tilde, which we use to obtain the reduced order basis. Now the randomization occur while generating this approximate basis G. And the basic idea is to draw k Gaussian random vectors and project them using the linear map of V cap. So intuitively, we are randomly sampling the range of V cap. And this is done something like this. So what we are interested in is this matrix, this approximate basis G, such that V cap minus G transpose V cap, norm of V cap minus G transpose V cap is less than some specified tolerance. And this is done as follows. First, we choose some k Gaussian random vectors and compute a matrix Y as V cap into G cap. Now, the orthonormal basis for this matrix Y is nothing but our desired matrix G. And this works because it is quite well proven that these k Gaussian random vectors are linearly independent. So the columns of the matrix Y are also linearly independent. So they spans the range of our data matrix V cap, and which gives us a proper orthonormal basis. And we can construct this G, that is this orthonormal basis for our matrix Y in the offline phase using Gram-Smith-like algorithm or QR factorization. And Halko recently published a really good adaptive algorithm based on this error norm to determine this G. And once we have our G, we can determine the left singular vector matrix and the reduced order basis, as I explained you before. Now let's talk about the sampling errors. The method which I presented you during this talk is the principal component regression technique. And this is a projection-based technique, so it has the projection error of the principal component analysis, which we can represent in the similar sense to the projection error of our proper orthogonal decomposition, which is nothing but the sum of squared of neglected singular values while selecting the P principal components. And in order to judge the quality of my developed surrogate model, I have used mean square error of prediction using k-fold cross-validation. So at each surrogate model loop, I have a learning data matrix L having CK parameters and the corresponding error estimator values. So for k-fold cross-validation, we divide this learning data matrix L into k-folds, which is represented using this graphic over here, quite well. So you can see I have some learning data matrix L, which I divide into k folds. Now I keep my first fold as a test set and the remaining fold as a training set. Now I keep on repeating this process for k iterations. And then finally, the mean square error of prediction is calculated by taking the average of errors over these k folds. And then the total sampling error is our projection error plus the mean square error of prediction. So all these algorithms I have tested for one interesting application of computational finance called financial risk analysis. So why finance is because actually model order reduction is a quite new and there are very few studies in computational finance, and my company Math Consult was quite interested in knowing how model order reduction or machine learning algorithms will behave considering a financial risk analysis application and considering the financial models. And that's why we considered this as the underlying application. What is the motivation behind financial risk analysis? So the risk analysis is usually performed to determine whether to undertake a particular venture, to know plausible returns, and how to mitigate an activity's potential losses. Now, in order to perform this risk analysis, we have to calculate value at risk or the expected shortfall to estimate worst case scenarios of that financial holdings. And to calculate this value at risk, we have to evaluate a financial instruments or a portfolio of financial instruments for a wide range of future market scenarios using some appropriate valuation function. which is quite computationally costly. In my work, I have used package retail and insurance-based investment product, in short called as PRIPs, which are generally offered to retail investors as stress example. There are different examples of PRIPs like floaters with caps and floor, callable, putable, stiffener, etc., which I will explain you in the next few slides. But before that, let's talk a bit about PRIPs. I have selected PRIPs as a test example for a multitude of reasons. First of all, the manufacturers of PRIPs have to obey PRIPs regulations prescribed by the European Commission. And according to these regulations, these manufacturers must provide key information document explaining possible returns and costs associated with the underlying investments. However, in order to determine these possible returns and costs associated with the underlying instrument, we have to solve that product for several thousand market scenarios, and which is obviously computationally costly, which creates a need for an efficient computational performance. And thus, I implemented my developed model order reduction framework. So there are different financial models, and usually the financial model is selected based on the underlying financial instrument. In my work, I have used convection-diffusion-reaction partial differential equations, and mainly I concentrated on two financial models, which are quite well known in the current financial market. The first one is the one-factor Hull-White model, and the second one, its extension, developed again by the Hull and White, called two-factor Hull-White model, as shown over here. These models are quite advantageous because of two things. First of all, you can see that these parameters A, B, and sigma, these are all time-dependent parameters. Similarly, in the case of two-factor model, parameter theta, alpha, B, sigma 1, and sigma 2 are time-dependent. And second of all, the second thing is currently means the European market has negative interest rates, and these models can treat negative interest rates. And these parameters, these model parameters, are usually calibrated using some market structures like yield curves. So you may know that the yield curve is a plot of interest rates versus different maturities or the time points. And in the case of PRIPs, the regulation demands to have at least 10,000 simulated yield curves in order to calibrate these parameters. And obviously, the calibration based on these 10,000 simulated yield curves generate a parameter set of order 10,000 cross m, where m is this number of 10R points or the time points of these yield curves. So you can see I had a problem of solving my financial models with such a large parameter set, and that's why I've implemented a model order reduction framework. So there are two examples at which I will present you today. The first one is a floater with caps and floor, and floater is an instrument whose coupon depends on some underlying interest rates. And caps and floor, as name suggests, put the upper and lower limits on the interest rates. I've solved this particular example using one-factor Hull-White model, which is discretized using finite difference method with Crank-Nicholson scheme for time discretization. The second numerical example is a putable stiffener, and stiffener is an instrument whose coupons depends on difference between two rates. So for example, in this table, you can see that the coupons between year 4 and year 10 depends on the difference between constant maturity swap rate at 10 years and the constant maturity swap rate at 2 years. And it is a putable type of instrument, and put is an option that gives the right to a buyer to sell the underlying asset at an agreed price in some time point in future. I've solved this putable stiffener example using two-factor Hull-White model, which is discretized using finite element method. So as I said earlier, we calibrate the model parameters using some simulated yield curves, and 10,000 simulated yield curves for 5 years and 10 years in future are presented over here. And this calibration based on these 10,000 simulated yield curves gives us our 10,000 parameter vectors. The results for the classical greedy POD approach are presented over here, and you can see that the projection error decreases monotonically with the increasing reduced dimension d, and the relative error is of order 10 raised to minus 4 with just a reduced dimension d is equal to 10. However, as I said earlier, this classical greedy sampling approach has some drawbacks, which is well depicted using these two figures. you can see there are some parameters, for example, number 238. For that, the relative error does not drop below certain value, even with the increasing reduced dimension. And this is a problem. And this problem is well overcome by the adaptive greedy approach, my developed adaptive greedy approach. And you can see that the relative error is already of order of 10 raised to minus 4, with just a reduced dimension d is equal to 10 for both floater and stiffener example. As I said earlier, in this talk, I have used principal component regression technique to build my surrogate model, which I have constructed with 5 principal components, as they comprise of almost 99.9% of the energy. And you can see that my surrogate model is working quite well, as it is as the real data and predicted data are within good approximation. Also, as I have used some approximate relative error model in order to monitor the convergence of my adaptive greedy sampling approach. And in my work, I have considered a linear model assumption. And with this obtained results, you can see that this linear model assumption is satisfactory for my 2 problems, floater and portable stiffener, as the coefficient of determination is already greater than 0.9. So let us talk a bit about computational cost comparison. As I said earlier, I've implemented randomized SVD, and you can clearly see its advantages. It is almost 10 times faster than the basic SVD. Talking about the evaluation time, you can see that the reduced order model obtained with the adaptive greedy POD approach of dimension d is equal to 10 is at least 20 times faster than the full order model approach in order to solve the entire parameter space P. And similar results are presented here for the stiffener. And you can see that again, the reduced order model of dimension d is equal to 10 is quite advantageous. It is almost 20 times faster than the full order model. So finally, we have to solve our reduced order model for the 10,000 parameters or this 10,000 yield curves for 5 years and 10 years in future. And these obtained 10,000 results are presented in the form of histograms over here. Now, in order to define this key information document, to design this key information documents, which informs to the investors that what will be the risk in particular scenario. And for that, we have to divide these 10,000 values into 3 performance scenarios, namely favorable, moderate, and unfavorable at 19th, 15th, and 10th percentile respectively. So as name suggests, this performance scenario tells investors, okay, in favorable condition, what will happen to my investment, or in unfavorable condition, what will happen to my investment. And this is the compulsory from the European Commission to provide to the current retail investors. And for comparison, I have presented the results obtained using a commercial software called Unrest, developed by my company MathConsult. And you can see that my reduced order model approach is working quite well. Similar results are presented here for the portable stiffener example. Here also the reduced order model is working quite well. So to conclude this presentation, I have presented parameter sampling approach based on greedy sampling algorithm. I have also presented an adaptive greedy sampling approach based on surrogate modeling, which can be used to overcome the drawbacks associated with the classical greedy sampling approach. And I've shown that only 10 full model evaluations are necessary for adaptively selected parameter groups in order to construct a good reduced order basis and to generate a good reduced order model. Also, the developed reduced order model is at least 15 to 20 times faster than the full order model approach. And the error analysis also provided a nice approach in order to select this grid size, then the number of sample parameters, and the reduced dimension, which significantly improved the overall model's output. So this whole framework shows a quite nice potential in financial risk analysis, considering the historical or Monte Carlo value at risk calculations. If you are interested, these algorithms and the codes are presented on the Git under the banner ROMSOP. You can check that out as well. These are our 2 manuscripts. If you are interested, you could have if you want to know more about the work. So finally, thank you very much for your attention. And now if you have any questions, please feel free to ask.
Thank you so much, Onkar, for your very nice and dense, I would say, talk. And there were lots of details there, and I'm sure that this recording will be very helpful to many of us, including me, to learn even more about your method. So I'm opening the discussion. Again, as usually, whoever wants to talk, just switch on your mic, possibly the camera, and just start talking.
Hello, Onkar. Hello, Jakub. Stefan here. I have just a very short question. How dependent on the type of PDE is because many of them you presented, the approaches you presented are. So how dependent are these approaches on the type of PDE, on the smoothness of the solution, and so on? Can you comment a bit on this?
Yeah, so the developed model order reduction framework is actually it doesn't much depends on what type of PDE you are using. If your PDE is giving a stable solution and if it's properly well defined, then the model order reduction framework will work because it's a projection and it's a linear projection technique. So whatever the reduced order model it is generating, it will be again also stable and it will give you the similar results.
Because I'm thinking of problems like, for example, either wave propagation problems. And that could be one question where I'm not exactly sure what happens because when I say wave, it could be electromagnetics or acoustics. It could be anything where you have the solution that can be looked for as a combination of, let's say, principal solutions. You can think of them this way, like a basis, and these basis functions, they may have they may be globally supported in a certain sense. So if you have an interval on 0 and 1, and then you can think of sine functions or cosine functions. And I guess if you do POD on that, then you'll try to find some functions which is like spectral analysis or something similar that is then going to be trying to recognize the content, the frequency content of these things. So that's one thing I'm wondering. And then the second type of problems where I'm wondering how this works is if you have, for example, something that a solution, let's say the solution is not so smooth. It's it's like I don't know, square root of t. Or it's 1 over t, or 1 over exponential alpha t with alpha greater than 1, for example. What would be, or even greater than 0 is enough, I think. So yeah, what would that? How would that? I mean, did you crash test your thing for cases where the solution isn't that easy to capture by a sum of basis functions? Do you understand what I'm asking now?
Yeah, I understand. Okay. So I actually didn't test it for this electromagnetic PDEs or as you described, these wave propagation problems. But what I tested my algorithms for highly advective PDEs. Okay. So there are PDEs, for example, let me explain you with this. Okay. So there are partial differential equations which are very advective dominant or convection dominant. My PDE is convection dominant, but it is still mild. And in that case, what happens is this projection error, the singular value decomposition has a weird structure. So it doesn't decay very fast. So you can see here the decay is very fast. And in that case, if these type of problems, or if there is some underlying, as you said, if the problem is very difficult to solve, or if isn't a smooth solution available, then there is a method called a shifted POD. So what it does is that it shifts your data matrix or that snapshot matrix with some corrector in order to get a smoother solution for the reduced order model. So it helps for the linearization of the reduced order model. And for that, I have tested my my developed model order reduction framework, which I didn't present it over here, but there are techniques to overcome these problems as well.
Okay, that's super cool.
Yeah.
Yeah,
You
I'm
could
just
check
wondering.
it out actually. The shift, it's
Yeah.
called a shifted POD approach. So if you're
Mhm.
interested, it's a really nice application and extension of the proper orthogonal decomposition.
Yeah, because it's not easy in what I saw in the past to do that thing
Yeah.
right. So yes, for things like hyperbolic equations,
Yeah.
probably it works, but if you sample over time as well as space, and if I don't know these very well, but I can show you. I can basically show you a few papers we wrote a long time ago on this, because it's been a long time. But for elliptic that have smooth solutions, I think it's kind of easy. Elliptic with tough, singular solutions or very rough solutions, I think it's not easy at all.
Okay.
And then for the parabolic, I think it's a mixture of elliptic and hyperbolic problems. So
yeah, actually you can implement POD in 2 steps as well, which helps you to overcome the problem involved in the time. I mean, time discretization if there is some anomalies in the time domain or in the space domain. So in what they do is that they compute the snapshots in the time domain first. They compute its singular value decomposition. They compute the solutions again in the spatial and the temporal domain. They compute its singular value decomposition, and then they combine those singular vectors in order to get more stable solution.
okay, that's super nice.
Yeah. So
Yeah,
these are
thanks.
there are techniques like these as well. So it's for my finance application. These PDs you can see these are linear PDs, and this was quite simple to solve, which I have presented in front of you. But obviously, I tested my algorithms for advection dominant, highly advection dominant PDs as well.
Yeah, already advection dominant creates problems, because if you have
Yeah,
Peclet number which is far greater than 1, then you have these boundary layers which will be difficult to capture with only a few basis functions, I think. So it's already.
That's why the
Cool.
shifted POD approach is usually used, and it is quite interesting actually when I first got to know about it. So if you're interested, read that. It's really interesting.
Yeah. Another approach that you may be interested in is the idea to split the domain either physically or temporally. Let's forget time for now and just take only space. One can actually, one did split the domain into subdomains and reduce each subdomain independently of the others, like Lego blocks,
Yeah.
So, and then each Lego block, you can have a different set of Lego blocks. So maybe some are, you can imagine cubic, and others are tetrahedral or spherical or whatever. I mean, of course, usually they are cubic, because what's the point of having weird shapes? And then you can even pre-reduce sometimes, so that each block has its own set of basis functions, but are all the same, and you just assemble them together. And in some of the blocks, you may lose the ability of the POD to converge fast, let's say, to the actual solution. So in that block, you may choose not to reduce at all and to solve the full PDE, but only in one block.
Yeah.
So that you keep the advantage everywhere, except where POD, in fact, is not really the right tool for the job. So in which case you use another method only where it's needed. That's also a possibility.
Yeah, that's interesting. That's an interesting idea. Actually.
Difficulty is when the thing moves, when the block that cannot be reduced moves around, because then you need, you need a lot of mumbo jumbo to link the moving block to the other blocks.
Okay.
So
I will think about this. Means actually there must be papers related to this as well, but I have to go through that literature. And
I can
nowadays
point you because we thought about specific problems where POD completely fails.
Okay.
And where you actually cannot use it. It completely goes out the window. But I don't want to bother everybody with that now. But I can send you I can show you actually better the paper. I think you'll be interested.
Sure. Actually, I guess you might have known that there are nowadays techniques which completely get rid of this reduced order model. So there are techniques called non-intrusive reduced order modeling, which replaces this dependency on the full order model on the reduced order model, which use some artificial neural networks or some machine learning techniques in order to replicate the full order model. So this is also something interesting. I guess one of the seminar we had in the machine learning, this machine learning seminar, one of the presenter presented this approach. It's called non-intrusive reduced order modeling, in which they use artificial neural networks instead of the reduced order model. So this avoids this dependency, and this is also something quite interesting. And I wanted to implement it for my problem, but due to some time constraint, I'm still working on it on the weekends whenever I get time.
It's okay. Thank you so much.
Yeah, no problem.
May I go ahead, Jakub?
Yeah, please go ahead.
Hi, Onkar. Thanks for the presentation. So,
Hi.
as Jakub said, the content was quite dense. I would just like to summarize what you said, and then I will ask the questions. Please correct if I'm wrong.
Okay.
So you said that you have some financial data. You first perform a principal component regression, and on that thing, you perform the POD and you explain the details about, let's say, randomized SVD and some other things. So is that right, what I said, first of all?
Okay, so you got some things right. So what I'm doing is, okay, let me show you the framework. So I don't know how much you know about the proper orthogonal decomposition approach. So this is not, so what it does is that once you discretize your model, you get some ODE or some linear system of equations, right?
Yeah.
So what it does is that it reduces this linear system of equations. So your matrices of order, let's say M in my case, right? So it reduces this system to D cross D.
Okay. Yeah, I know about POD, that you basically get the reduced basis to represent the full space. But then you also talked about some PCA there, and I got confused. I got mixed by.
Yeah. So the thing is, we have to determine this reduced order basis, right, in order to generate a reduced order model.
Yeah.
And this reduced order basis is obtained using some snapshot matrix, which depends on these parameters, which we use to obtain the snapshots.
Yeah.
And my method is, I'm mainly concerned with how to select these parameters.
Yeah.
In order to get a better reduced order basis. And that's why I'm implementing this. So the thing is, you have to solve, usually the classical methods, what they do is that they solve the error estimators. So for example, here this error is this residual error, right? So if you take the norm of this P, then it will be a residual error, right? So they solve this residual error for the parameter space, and they determine which parameters are giving us the maximum error. And you can intuitively think about it. If you already put the information related to the maximum parameters which give you the maximum error into your snapshot matrix, so you will get a better reduced order basis in the next iteration, right? You are eliminating those parameters. And that's why to select these parameters, but this is costly. You cannot solve the error estimator for the entire parameter space, right? Because it involves solving the reduced order model, and this is useless. What is the use of this? So that's why I replace this error estimator with some surrogate model, and this surrogate model I have built using principal component regression technique.
Okay.
And here the PCA again takes place. I should have explained the KNN or something, because I understand this is a bit confusing, that POD is again a projection-based technique, and the principal component is again a projection-based technique. But why I explained the principal component regression was because of this overfitting problem. And you might know, you work with the machine learning, so it replaces the M variable with P principal components. This is
Yeah,
the idea.
okay.
This is the overall idea. I hope you understand what I wanted to say.
Yeah, now it's a bit more clear because it got mixed up earlier. I did not get why you used
Okay.
two techniques at the same time. And
I thought that as well while designing this presentation, how much people know about this POD and the model order reduction. Okay, I should have explained a bit more in the model order reduction sense. Thank you
because
for the input. I will do it in the next talk. Yeah.
what I thought that then basically you are enforcing the linear constraints on your data, and then I did not follow at all. I got confused a lot.
Okay. Yeah, I felt it while designing this presentation that okay, I'm putting a lot of things into a single presentation. I guess I should have explained a bit more details about model order reduction as well. Okay, I will take this note into account.
Okay, thank you.
Yep.
Onkar, maybe following this question, could you just because there are two parts of your presentation, the let's say theory or your methodology, and then the example. Can you somehow, using your example, show at the example which animal in your example is the symbol in your methodology? Let's say, what are the snapshots? What is the unknown? What is the controlling parameter that you are searching for?
Okay.
Because it will be maybe much easier to understand it, at least to me. But
Okay.
in particular, you have some time-dependent parameters here on this slide, which are perhaps the ones that you are searching for, trying to identify, or maybe these are given by your data. This is what I am not sure. What is the variable of the model? What are the variables that parameters that you are searching for? And that would be much more easy to, let's say, capture.
Okay, so we are solving for these financial models solve the instrument. So here denoted with the V. So this is my output from my PD. And what I'm doing parameter sampling on this parameter A, B, and sigma in case of one factor model. So these are my parameters.
But these are time dependent, right? So
yeah,
you are
these are time
sampling
dependent.
over.
Actually,
So you discretize the time, and you have a number of times steps, and you sample these values per each time step, right?
Yeah, per each time step. And actually,
and then you are solving. Okay.
Yeah, the thing is, actually, these parameters are not, these are actually piecewise constant parameters. So in finance, they are considered piecewise constant. So you can see, okay, so this is not a bit clear from this, but these are considered piecewise constant. So between, let's say, if I consider, so for my problem, the maturity was 10 years, right? So consider each year has some 360 days. Okay, so there are so the your time domain will be divided into 0 to 3660, right? So these parameters are not for each time point, so they are not varying from 0, 1, 2, 3, not like that. So they are varying from, let's say, from 0 time point to 20 time point, then from 20 to 40 they are again constant, then 40 to 60 they are again constant. So they are piecewise constant. Yeah, so this is it, and we are solving for this any instrument, whatever the instrument is. And there are some other boundary conditions associated with it. It's not boundary conditions, but the conditions, you would say. I would not say it as boundary conditions because I've used homogeneous Newman boundary conditions, because don't know the value of the instrument at first for that particular interest rates. So you cannot put the discrete boundary conditions. But there are conditions like cap rate or the floor rate. As I said, the cap and the floor put the upper and lower limits on your interest rates. So you have to monitor this while solving this particular PDE as well. That if the interest rate shoots over some particular value, then you have to put the cap on it. Then you have to put this 0.225 as the interest rate. You cannot put 0.226 as the interest rate. So it's like that. So there are some other things as well, other integrate things as well.
But I can imagine that some of these parameters are not controlled by you. These are like external uncertainties that are must be introduced into the model. And then how can you sample them properly? Do you have any insights? What is the, let's say, probability distribution for those parameters that you can use to sample this properly? Or you just giving a chance with some Gaussian or whatever else you can come up with?
Yeah, I understand. Okay. So these are all, so if you consider the distribution of these parameters, then this is always a bell curve. It's always a bell curve in finance. And these are usually calibrated, means in my work at least, I've used, I should have explained it somewhere. Okay. So these are calibrated using unrisk pricing engine. So it is the software developed by Math Consult, my company. And it solves regularization problem using Tikhonova regularization. I don't know whether you know this. So it's an inverse type of problem. So in order to calibrate these parameters, you have to solve some linear system of equation. But that linear system of equation is very highly unstable, as you said, right? Because of some noise in the historical data. Because this market structures, yield curves are the historical data, and there might be a noise in it. So to dampen this noise, they solve the inverse problem using Tikhonova regularization, and whatever these parameters you get, these are very stable. Because means people have spent a lot of time. Means this is from 1980s. These models are from 1990s and 1980s, and that's why whatever the parameters you get, these are very stable and well represented using the bell curve. So there are no anomalies if you solve it properly. And this is already done in the pricing engine.
Okay, so in a very general way, I understand how it is.
Yeah, actually, yeah, this is also quite complicated process, calibration of parameters, which wasn't the interest of my study. So I tried to avoid it, but I know everybody asks me questions, how you calibrate these parameters, how stable they are, is there a noise involved in it? But there are methods to overcome these problems as well.
I see. So any more question?
Hi, Jakub, this is Eleni. Onkar, congratulations on your talk. It was super clear and I really enjoyed it.
Thank you very much.
I know that this is something you didn't touch upon today, but I would like your comment on how this methodology would perform, if it would perform any differently in the case of a highly nonlinear PDE, where when you derive the reduced order model by doing projection, then you end up also with a term that is large and somehow needs to be addressed. I know that this is not exactly the topic of your work, but maybe you have an idea of.
Yeah, I could comment on it. So if it is inherent non-linearity in it, then the POD approach works quite well. But if there is some external non-linearity, then there are methods called as discrete empirical interpolation methods, which treats that non-linearity separately. So what they do is that, for example, there is some non-linearity over here, consider it my PD. So what they do is that they treat that nonlinearity, they generated separate reduced order basis for that nonlinearity, and then they solve the linear part separately and the nonlinear part separately. And then they combine the solution. And this is all done in the offline phase. Computing the reduced order basis for the nonlinear part is again done in the offline phase.
And in terms of your methodology in combination with this nonlinear PDE and discrete empirical interpolation or whatever, Does it work in exactly the same way? Do you have to apply some changes?
No, it will exactly work in the same way, just that I would have to incorporate the discrete empirical interpolation in my work. That's it. So my framework, okay. This is the framework, right? So I just have to incorporate a discrete empirical interpolation over here with the POD, and then it will work in the similar sense. Hello?
Yeah, and in terms of performance?
Okay. So the problem is, if you consider this discrete empirical interpolation, then again you have to perform a new singular value decomposition in order to obtain the reduced order basis for nonlinearity, right? So this is bit computationally costly. So you have to perform the singular in the offline phase. I'm not talking about the online phase. In the offline phase, it is computationally costly than the normal POD because you are performing the singular value decomposition twice and you're solving the nonlinearity separately. So this is sometimes quite computationally costly, but this is all related to the offline phase. But considering the performance or the merits, all the defined error estimators for the POD works well with the nonlinearity and with the discrete empirical interpolation as well. And this is well done study in the fluid mechanics or fluid dynamics. And this POD approach is actually coming from fluid dynamics. So this will work quite well.
Hey, thank you again, and thank you for your talk.
No problem.
Okay, so we have a time for a very short question, if there is any. So if not, thank you very much, Onkar. I'm really happy to have this nice presentation today and very nice discussion as well. And next week we'll probably will not have a seminar. Okay. And I will inform you about the incoming seminars, and I will send invitation as usual. So thank you so much again to everybody, and have a good day.
You too. Bye-bye.